Hello, good afternoon, everybody. Welcome back to our second day of the Machine Learning in Science conference. I'm very happy the way the conference went yesterday. We had lots of interesting talks. We had lots of participants and people who watched the conference both on Crowdcast and on YouTube. Today, we also have a very interesting program for the full day. So it's going to start by a talk by Peter Dayan, who's already with me on the stage. Then we are going to have a presentation by Dominic Papis from the Economics Department. After a short break, we are going to have spotlight presentations again by people from the internal projects of the Cluster of Excellence. And then there are two more invited talks, one by Ingo Steinwart from the University of Stuttgart and one by Claire Montaglioni, who is currently at the University of Colorado in Boulder. So I think we simply get started. Before I introduce Peter, maybe the one important thing, if you want to ask a question, please do that already during the talk. It's much easier for myself if I can monitor the questions already during the talk and sort of bring them into a useful order. I realized yesterday that this is quite difficult if I have to do it right on time when I'm supposed to ask the questions. So please already ask your questions during the talk. There's at the bottom right of your screen, there's a little button that says ask a question. You can ask a question. And everybody else who doesn't want to ask a question, you can also vote on the questions and vote them up or down, depending on how important you find it that I'm going to ask this question. Other than that, I think everything is sort of self-explanatory, so it will simply work. Okay, so then I'm very, very happy to introduce Peter Dayan to you as our first speaker. Peter Dayan, of course, is a very well-known person in our community, and I think he doesn't need a lot of introduction. He was one of the co-founders of the Gatsby unit in London, which is one of the big famous labs for machine learning and computational neuroscience in the world. He's been there for about 20 years, and then we were very, very lucky that Peter moved to Tübingen and to become a Max Planck director in the Institute for Biological Cybernetics. So we are very happy to have Peter around. He has won numerous awards, and I'm not going to mention all of them. He's working on the area, on the intersection between machine learning and computational neuroscience. And today he's going to talk about the modeling and manipulating behavior using recurrent neural networks. So please start, Peter. Thanks for coming.
Great. Thank you very much indeed. Thank you for this invitation. It's a really great pleasure to be here. So one of the pleasures of doing a conference in your own hometown is that you don't have to travel very far. Of course, this time it's just my bits that don't have to travel very far. So the work I'm going to talk about today is actually based on a number of papers. Many of them have been, all have been led by Amir Desfouli, who's a researcher at CSIRO in Sydney in Australia. And then parts of this are joint work with Bernard Belain, who was Amir's PhD supervisor, Richard Morris, a colleague of theirs, and Richard Nock, who's also at CSIRO, and then some other colleagues as well we've worked jointly on together. So the plan for the talk is, I'm going to start talking a bit about how we sort of model complex behavior using recurrent neural networks. I'll say a word about how we used to do, some of the ways that we do it, and some of the ways that drove us to using recurrent neural nets as a route along that way. Then I'm going to talk about how to characterize complex behavior using this slightly word salad, auto-encoding hypernetworks. You'll see where those come in this context shortly. And then I'm going to talk about how we can use our ability to model behavior to try and exploit it. And here we're going to use a form of reinforcement learning to try and build a sort of exploitation device that we can use to exploit the way that human subjects or other models actually perform in a task. So to introduce this, I'm going to tell you about a behavioral study that was carried out in Bernard Belain's lab, which is a very simple two-arm bandit task, which goes like this. So subjects were faced with a screen where they had two choices, either left or right, and then they were faced with 12 blocks, in which they had 40 seconds in total to make choices between these left and right bandits. So it's a very fast-paced task, essentially, and each block is 40 seconds, and the subjects made around 110 choices during that session. So they're making choices in order to get either M&Ms or another sort of food stuff that they're going to earn during this time. And the reason to choose one bandit or another is a function of the probability that the bandit returns a reward. So here there were three different probabilities: 0.25, 0.125, and 0.08. That's for one of the bandits, and then the other bandit was just 0.05. So none of these bandits are returning reward on every trial by any means. So the richest bandit is only a quarter of the time. And so therefore subjects are going to have to explore to find out, which ones they should use. So we had 3 groups of subjects with unipolar depression, subjects with bipolar depression, and then healthy subjects as a control. And in fact, all the subjects made about the same number of choices. There are some details that I won't go into for the moment. So what happens in this sort of task? So what this plot shows you is the probability that the subjects chose the best action, so here the correct action, over the course of, this is averaging over these blocks with these different probabilities. And you can see that our healthy subjects did a little bit better than our depression and bipolar subjects, and they're still not choosing the best action all the time, because of course they have to learn, and there's an exploitation trade-off, as always in these sorts of bandit tasks. So that seems fairly reasonable, although performance, you could hope for better performance perhaps. What's unusual about this, which I'm going to call them bizarre bandits though, is that if we look at the stay probability, which is to say, what's the probability that having chosen left, the subjects choose left the next time, as a function of getting reward on left or getting no reward on left. What you might think is, in this sort of context, that if you got a reward, like a good reinforcement learning agent, what our subjects should do is to be more likely to repeat a choice that was rewarded. So expect a stay probability that was high. And what you can see here is the stay probability is actually significantly higher on the no reward cases when they didn't get reward than on the case where they did get reward. So that's true for the depression subjects. What about the others? So we look at the bipolar subjects. In fact, there's a small trend towards that, but it's not significant. You think, well, maybe something special about depression. So then we looked at our healthy subjects, and then woe betide us. You can see that it's much stronger even than for the depression. So you see a very strong case where the subjects have this tendency apparently to do a sort of switching. And we can imagine there might be a sort of gambler's fallacy in which the subjects are unwilling to, if I got rewarded this time, maybe I'm not going to get rewarded next time, even though that, of course, is not the way that the task actually is designed. Okay, so we have to model this behavior. So the way that we would normally do this modeling, I think, was nicely reflected in some of the talks yesterday. You'd build a sort of simulation model of the way the behavior works and then fit that to the data. So what would a simulation model contain? Well, a sensible way to do it might be to use Q-learning. So this work from Chris Watkins from 30 years ago. So here you'd say, I'm going to have some Q values, which is the value of choosing one of the actions, so left or right. And then you update that based on the reward you get. So if you choose it, you update with a learning rate here, which is phi, based on getting a reward or not getting a reward. So we generate this as our simulation model, and then use maximum likelihood or a Bayesian method or one of the sophisticated methods you heard about yesterday in order to fit this model. And then we would then choose the going left or right using a softmax, or in this case, it would just be the same as using a sigmoid function. So where we favor those actions which have a large Q value, so going left if left has a large Q value, with an inverse temperature parameter beta, which tells you by how much we prefer it. So a slight addition to these models, which is often important for modeling behavior, is to note that our subjects sometimes perseverate or alternate, which means that sometimes they chose left last time, they'd like to choose left more next time, or choose right more next time, independent of whether they got a reward or not. So these are sometimes called perseveration or alternation kernels. And we can model that by having a term K of T, which is just the value kappa for the action that you chose last time. And then we can just add K of T to the Q values, which means that we can either, if kappa is positive, it means you prefer to choose again the same action you chose before. If kappa is negative, then you prefer to alternate. We can also use a generalized linear model, which we're going to call LIN, where we essentially look at the log likelihood ratio of choosing left versus right, and just fit it by a linear model of the actions you chose, which has this kernel effect, the rewards that you got, and then an interaction term, which is how you can cope with the fact that you chose left, you got a reward or not. And we can then sum up over a number of trials in the past, so capital J trials in the past, and it turns out using cross-validation that 18 trials in the past was the best number of trials to use in this particular context. Okay, so there's some sensible models, and how do they do in terms of fitting behavior? So in terms of fitting the probability of selecting the best action, the Q-learning does a reasonable job. The other models don't do such a great job of replicating that. And what you can see is that they particularly struggle, and you can imagine that Q-learning in particular is going to struggle mightily with this phenomenon I showed you, which is that the subjects prefer to reject an action that was rewarded. So Q-learning, if you have a positive learning rate, is going to favor the actions that were rewarded before. And it turns out that when you fit Q-learning with perseveration, that kappa, same thing happens. The linear model can do a slightly better job of fitting it, but it doesn't capture anything like the normal range of our subjects, even though it's fit on a subject-by-subject basis. That's true for the healthy subjects. Same thing is true for the depressed subjects and also for the bipolar subjects too. So there's something we're missing in these models, and that's what we were set out to try and avoid. So the other end of the spectrum in this modeling world is to go for a much less constrained model, which is capable of, one hopes, of fitting all the structure of behavior. And then instead of having these well-defined parameters, we now have a set of parameters of strong or complicated parameterization that we can then, but at least we can get a good characterization of behavior. Then we can worry about how it is we can use this characterization to interpret the behavior that we see. So in this world, what we have is some sort of recurrent neural network which consumes actions and rewards, so the actions the subjects chose and the rewards that they received, and spits out a probability that the subject on the next trial will choose left or right. So it's the same idea as the Q-learning model that we showed you before, but now we have a big recurrent neural network that can choose to do all sorts of rich things, nonlinear things with the data that it has. So in this context, we actually use LSTMs, but in a later paper, we're going to talk about using GRUs. So any of these standard mechanisms that people use. And so now we have a very large number of parameters. So we tried different numbers of these LSTM units, little storage units, which store information from the past. And so we have somewhere between a couple of 100 and a couple of 1,000 parameters. It turns out for the healthy and the depressed subjects, 10, so these 600 parameters works best. For the bipolar, a few more, again, using cross-validation where necessary. And then we fit these models using the same cross-validation, so using the same log likelihood cost function that we use for the Q-learning models as well. So we're trying to fit the probability that they make those choices. And now what you can see is that these models are going to do a lot better, which is just what you hope, because they have this greater capacity. So here you can see in terms of the probability of selecting the best action, the RNN does a pretty good job of modeling the subject's data themselves. And then for all the classes of subjects, here I'm just comparing it against the Lin model, the GLM, because the Lin model was the best in terms of fitting before. And you can see that the RNN does a better job of does a good job of characterizing this strange phenomenon I talked about, where they prefer to switch after a reward. And you can see that for the depressed subjects and for the bipolar subjects too. And in particular, for the bipolar subjects, the linear model is really struggling, which you can see by the fact that for each of the subjects is really compressed to a very small range of predictions, a small range of parameters, whereas the RNN is capturing something of the variability amongst those subjects, I think, in a slightly richer way. We can then look at how well it fits in other ways. This is a negative log probability, averaged, again, over the cross-validation cases. You can see the RNN does better than all the other models. And then also looking at the percentage correct, so the percentage that the model gets correct in terms of predicting human choice. And again, you can see that's true for all the healthy, depressed, and bipolar. Again, using cross-validation, this model is doing better. So, of course, we now have captured this behavior in a complicated way. Can we learn anything about the structure of how they're making those choices? So here's some of our attempts to try and, a couple of our attempts to try and do that. So here what I'm showing is off-policy simulation, which means that I program a set of actions and a set of rewards, and then we look to see what the model returns as the probability that the next choice would be either right or left. So here, for instance, I chose 10 right choices in a row, followed by 20 left choices in a row. And I'm showing the probability of selecting left. So that's high if the probability of left is high. And then these crosses are where a reward is given. So I choose a reward. And what you can see is this negative effect that we talked about. This is then looking at what happens to the RNN, this LSTM network, which when you get a reward, you get a dip below, in this case, just below 0.5 for the probability of choosing the left action. So even though you got rewarded for left, you're less likely to choose left, which is exactly what we saw before. You can see the linear model has a very similar effect, but to a rather smaller degree. And then the Q-learning models are just incapable of capturing this phenomenon, and they have a very odd, unusual pattern that then obviously just simply doesn't fit the data very well. We can look now what happens if you make it more complicated. So now I've added an extra 1 reward, or here an extra 2 rewards. And you might ask yourself, well, how is the model ever going to choose well, or our subjects ever going to choose well, if when they get a reward, they prefer to choose the other action? And you can see that here, what happens is as they get more rewards, more and more, the extent of the dip is rather smaller. And you can see that there are also interesting dynamics that have to do with how long they've been choosing right here. That in fact, the first dip is also much smaller than this dip here. And you can see there's even a slight decrease over time, indicating that the model has a slight tendency to want to switch over these times. And the other models are not so capable of capturing these sorts of dynamics. And then we can look at just using the recurrent neural network as a function of disease status. So here, this is what I showed you before for the healthy subjects. Now, if you look across the depressed and the bipolar subjects, and you can see in particular that the extent of the dip, now this is averaging the parameters over those subjects, you can see the extent of the dip is much lower in the case of the bipolar subjects. And also there are other phenomena going on with the bipolar subjects to do with this this effect. You can see that their incentive to try and switch is rising over around 10 trials after this first 10 trials that we had. So here they're more likely to choose right, they're getting a bit more likely to choose right rather than left. So we can look at that switching in another way and ask for the subjects and for the models. We can ask, as a function of how many times do they choose one way, let's say it chose left 5 times up till now, how long is the length of a run in the next time? If they switch from going left to going right, we can ask how long is the length of the next run if they chose a run of 5 before. And what you see is that our subjects and the RNN have an interesting pattern of behavior here, which is not captured by the linear model. And in particular, what you can see, for instance, in our bipolar subjects is it looks perfectly linear, which means that if they had a switching of 2, it would mean they had a run of 2, they'd like the next run to have an average of 2. They had a run of 4, the next run should have an average of 4 too. And that means that we expect to get symmetric oscillations from our subjects. And indeed, that's exactly what you see when we look at what happens in this model. So here, I provided some off-policy choices, so right for 6 choices, then followed by left, right, left. So we're engendering this switching. And you can see that the RNN, then when we leave the model to choose by itself, it then shows this switching behavior. And that actually is something that we expect to see in the subjects too. In fact, we get that in the subjects also. Okay, so some interesting conclusions from here. So existing methods fail to capture the structure of behavior well. This new method predicts choices without the manual engineering that we had. We just have a rather generic network. So at the least, it gives us a baseline for the predictive accuracy for proper models, so mechanistic models like the Q-learning model. Here's what we're missing. We know we can fit this. You should be able to fit that too with another model. It turns out to be representative of group behavior, because we can see that in these off-policy simulations, things like the observations. And we can also use this model to predict diagnostic labels weakly. It's not a very good way of predicting what the diagnostic label for the subjects is, but that shows that we have some capability of predicting what's going on with them. And note that we're not trying to predict how to do well in the task. We're trying to predict how subjects perform in the task. We're interested in modeling the subjects' behavior themselves. Okay, so the next part is to think about how can we characterize complex behavior. And here what we're going to do is to use a sort of autoencoder. So you think about what we've discovered is that there are clearly some structural regularities in the behavior that we have. And so what we'd like to do is somehow compress the way that our subjects make choices to give us a nice low-dimensional representation. And Q-learning does that. It has a learning rate, an inverse temperature, and maybe that a lapse rate, so a property of just like a trembling hand. And that means we have only 3 dimensions to characterize however many 100 choices we had. We had 1,200 choices before. But of course, Q-learning didn't do very well. So maybe what we'd like to do is to build a sort of autoencoder architecture, which then allows us to get some insight into the choices that happen. So here, the encoder should consume the behavior of individual subjects and spit out a set of low-dimensional representation of that behavior. So maybe like the 3 parameters of Q-learning or whatever parameters it can come up with. And then a decoder takes those low-dimensional coordinates and then spits out a behavioral algorithm, a characterization of the way that our subjects themselves would choose on subsequent occasions. So how's that going to look? We have our input sequences here for capital N subjects being fed into this RNN, which is an encoder RNN, which in the end compresses it down into a small number of dimensions, 2 dimensions, 3 dimensions, or so forth. So it gives us a latent space where one point in that space is supposed to characterize the algorithm that that subject uses to make all the choices that that subject emits. And then we have a decoder whose job it is to take this low-dimensional representation and then spit out an algorithm. So the way that we make that decoder work is to have it spit out essentially the weights of a neural network, of one of these actually a GRU network, which means that here we can think of this decoder as being a hyper network, because it's not predicting behavior itself, it's predicting the weights of another network, this GRU network, which then predicts behavior itself. And what we need to do then is to specify a set of cost functions which are going to allow us to generate a good quality characterization of this behavior. So it turns out that the cost function we're going to use has three components. One is just a reconstruction loss. So how well can we, when we run this behavior, this decoded behavior, how well does it characterize what our subjects actually did? Another one is a sort of disentanglement loss. We'd like this representation to have this latent representation to have some nice simple properties. So for instance, we'd like to have a sort of disentangle the underlying dimensions of variability. And then we also going to have a separability loss, which is going to encourage the network to separate out different sorts of effects in this case, the two coordinates, Z1 and Z2. So what do those look like? So reconstruction is just the log probability, nothing exciting there. For disentanglement, what we did is to imagine that we'd like a prior distribution in the latent space, which is maybe an isotropic Gaussian with some standard variation, some standard variance. And then we actually used two components of that, a sort of KL divergence between a matched Gaussian for the empirical distribution we come up with in the latent space. And then we used also a form of MMD as another way of measuring the discrepancy between the distribution that we came up with and the isotropic prior. So these are just ways of saying we'd like to have nicely disentangled distributions in the hidden space. And then we wanted separability. And what we mean by that is that we'd like Z1 and Z2, our latent dimensions, to have very different structural effects on behavior. So one way of characterizing that is to say, let's look at how the logits change as a function of Z1. So here, the logits are the probability it's like the log likelihood ratio of making a choice left or right in the Bandit context. That's how it changes with respect to Z1. We'd like the way that it changes with respect to Z1 not to be affected by the value of Z2. So you could characterize that one way is by the second derivative of this logits with respect to both parameters. And then we actually, as it turns out, for speed, we use an approximation to this, where we essentially, again, encouraging the network to separate out the various effects that we see. Okay, so on a standard Bandit task, we can ask, how does this work? This is now a regular Bandit, a bit like the Bandit I showed you before. But now we can ask, if we just train the network on Q-learning with different values of the inverse temperature beta and this perseveration parameter, we can ask for instance, in this case, for Q-learning itself, we can ask in this off-policy case where we're choosing one action, so C1, like choosing left every single trial, what's the effect of a reward here at this time? And then here we're keeping beta 3 and varying kappa. Here we're keeping kappa 0 and varying beta. So you can see that when you vary beta and you give a reward, Q-learning, of course, gives you a big bump in the probability of choosing that action. And the size of the bump is proportional to beta, because beta is like the inverse temperature. Whereas if you look at what the effect of kappa is, it's just a generic effect in terms of perseveration, positive kappa, or switching, negative kappa, which then sits on top of the reward effect. And then when we train our model on Q-learning, you can see that it extracts into Z1 and Z2 by itself. It extracts something which very much looks like the effect of beta here for this Z2 parameter and kappa here for Z1. So it was able, in the case of Q-learning, to extract a low-dimensional representation which looks like Q-learning. This looks like a success of the model. And then here you can see this disentanglement. So here I'm showing you Z1 and Z2 as a function of kappa and beta. You can see that Z1 indeed captures kappa and doesn't show any much relationship to beta. Z2 captures beta, albeit slightly non-linearly, with no relationship to kappa. So we've basically succeeded in this context. If we now look at our three population sample, so now we just then trained our model, the same model on all the data. We didn't split them up into the individual groups, but now I'm showing you what it looks like. you can see that they split nicely on this. They give you an interesting axis in Z1 and Z2. See, bipolar actually looks like there's almost like 2 or 3 different potential clusters. So we'd like to look at that in more detail. It looks like now when you look across the whole population, Z1 doesn't seem to covary much with healthy depression or bipolar, but Z2 very much does. And if we then do the same sorts of plots now, both either off policy or on policy, so off policy, we're always making it choose C1, asking the effect of reward. You can see that you can see the effect of changing Z1, which has some sort of reward effect, and changing Z2 has a huge impact on this sort of switching-like behavior, so the propensity to choose a different action next time. And if you run the model on policy, so it's choosing its own actions, you can see that again, as we get these very negative values of Z2, you can see that, which are the bipolar subjects are overrepresented, you can see that the model starts to show this switching behavior all by itself. So Z1 is sort of weak reward sensitivity, Z2 shows switching, but we haven't got perfect disentanglement in a sense. You can see that the effective reward is small for large values of Z2, and it's large for negative values of Z2. Okay, so conclusions of this are, again, this gives us a nice flexible framework to look at individual differences. We fit all the subjects into the same model, and we have these sort of essentially a meta learner. So our algorithm is now capable of solving these reinforcement learning tasks, and we have this meta learner as a hyper network. And of course, we can think about different ways of doing disentanglement. That's a very hot area in machine learning at the moment. We can think about other ways of other abstract characterizations of the behavior, for instance, using reinforcement learning. And then it would be interesting to look at generalization to other tasks. So train the network on multiple tasks simultaneously and see how the subjects generalize. Okay, I'm running a bit out of time, but I'm going to say a few words about how we can exploit this, use the same ideas to exploit subjects instead of look at just learning about their behavior. So here the idea is, if the model can capture the rules governing behavior, can we learn how to specify reward distributions, for instance, or something about the rewards in order to exploit it maximally? So we do the same thing. Here, our subjects normally would perform a task. They choose actions, get rewards, and we'd do that. And then I just showed you how it is that we can learn how to characterize their behavior using these recurrent neural networks, for instance. So you learn about the subjects. And then what we can do is to couple this learner with an adversary, which, for instance, could receive information about the hidden state of our learning network, which is what we believe to be some characterization of the hidden state of the subjects, and then can figure out, using a reinforcement learning algorithms like DQN or A2C, what rewards to get what rewards to give to the learner in order to maximize some cost function. So for instance, to push our subjects around in the maximal direction, or to make it the cheapest for us to exploit the subjects, or to push some other aspect of their behavior. And then, having learned this adversary, we now can use the adversary to feed these rewards into a subject and then see what the subject does. And then again, use our learner, for instance, to work out what we think the subject is thinking at that particular time in terms of the way that we characterize their behavior. So we did this on a couple of tasks. I'll just show you the Bandit task because of time. So here we had so basically it's like a non-stationary 2-arm Bandit. It's non-stationary because our adversary in the end is making choices. And we're using an idea that comes from Dan and Lowenstein, who basically did this as a prediction competition or a choice competition for subjects. So they used a very big value of beta. So this inverse temperature was very high. So we have 100 trials, and the idea is you're trying to get the adversary to make subjects choose left as many times as possible. And we make it be fair by saying they have to program 25 rewards on left, 25 rewards on right, but the adversary gets to choose when to give those rewards in order to try and push the subjects around. So we're thinking about what happens is shown by this plot. Here, what you see is these dots are when the subject chose left or right. So red is left, and red is right, and blue is left. We're trying to make this be blue. And then blue says, when did the adversary program a reward? So if the subject chose blue, on that case, it would get a reward. If it chose red, it would not get a reward. And we forced there to be 25 upward going blue arrows and 25 downward going red arrows, red lines, which say those are the 25 rewards we have. And what this model is showing you is the probability that we think our subjects are going to choose left, that our learner model tells us our subjects are choosing left. And you can see here that the model was fantastically successful. That's to say, now we're playing Q-learning, so that should be fairly easy. So Q-learning here, it chose red first. We didn't pay that reward because it didn't choose blue. Next time Q-learning chooses right, chooses the action we care about, the target action, that was actually rewarded by us. And then we think that Q-learning is going to keep on choosing that choice no matter what. And that's exactly what happens. And so we have this nice high performance over that time. And then by the time we're having to give rewards in the red case, our subjects have already been highly biased, or Q-learning has been highly biased in favor of the other action. We did the same thing on human subjects. Now, human subjects, of course, were very much unlike Q-learners. Here, this is some data that Dayan and Lowenstein collected, so 484 humans. And here, we're showing again that our model is capable. In this case, it programmed a lot of rewards at the beginning for blue. It was so sure that the subjects were going to choose blue that it can now essentially waste the red rewards here because it doesn't think the subject's going to choose those red rewards anyway. And then it moves into this sort of partial reinforcement time here, where it's only occasionally rewarding the other action. And then when the subject made when the human made a bad choice, then we have to correct it, and it does that by spending some more rewards on blue in this case, that it then allows the subjects to keep on choosing blue again, which is what we wanted. Okay, so I'm running out of time, so let me just not forget about the go-no-go task. So the conclusions of this part are we've sort of distilled the cognitive biases that we think our subjects have. Now, of course, we just did one case. We just trained subjects randomly, and then we trained our adversary on the random behavior. Of course, we could do one more round of training and train our adversary on the behavior that was elicited, a new adversary on the behavior that was elicited from the old behavior, because there's a sort of covariate shift problem that's obvious here. And of course, there's nothing new here. You know, people have been manipulating behavior forever, but this is nice to see this using these recurrent neural networks as a way of looking at it. And now we're looking at other tasks too. So just to sum up, what we've argued is that these recurrent neural networks, like these LSTMs and GRUs, are flexible characterizations of behavior. We can predict, we can disentangle their behavior, so find underlying parameters, and we can try and exploit the choices they make. So individual differences are completely central to this. We get a rich characterization of those differences. And that allows us, for instance, to do classification, but also to exploit individual ways that they behave themselves. Of course, understanding remains a sort of bespoke game. So I showed you these off-policy simulations. Those are, of course, are slightly limited ways of the rich understanding we might hope to get in other cases. So we're thinking about how to do that. And the small number of dimensions, of course, is a big important route along those ways, because we can then say what happens in that dimensional space, what sort of algorithms we generate using our hypernetwork. We've also done this, we've used the same ideas to link neural signals and behavioral signals together, both in fMRI and also using, currently we're doing that using neuropixels probes, so data from rodent studies. And then we're also doing, at the moment, doing some work where we're trying to get a better insight into what happens by trying to find sort of prototype subsequences. So what is it that the models are sort of able to characterize about the behavior themselves? But I haven't got time to talk about that. So thank you very much. I'm very interested to hear your questions.
Thank you very much, Peter, for your talk. I already saw a lot of questions coming in the question box, and I'm also encouraging people to ask more questions now. In the meantime, I'll try to start asking the first question. So the one that received the largest number of votes currently is following. So it asks about the population of bipolar patients, and it asks in which mood they have been when this data was recorded. What have they been in maniac or depressed mode, and whether this would make a difference, or whether the linear model would have an easier job if you would know about that.
So, the patients were not in a, they were being medicated. They were medicated, so they were in controlled state. So they were not in a manic phase or a depressed phase at the time that they were doing the study. However, absolutely, we would definitely expect that there to be a state effect in terms of what state they're in terms of the disease. And if our model knew that, it would help. Of course, what we might hope is the model would be able to detect that. So, for instance, we trained the model. You can imagine if we had subjects in different states, and we trained the second approach that I talked about, where we have this low-dimensional characterization of behavior. We might hope to be able to get to elicit a parameterization of the behavior in those different states that the animals, the patients would have, and that would give us a characterization of the sorts of choices they're having. So we had not expected this switching sort of behavior. So as you can see, this bandit elicited this particular sort of bandit that Bernard ran. Elicited a different sort of behavior than we normally get from bandits. And actually, it would be really interesting to go back and now take the same subjects and do other tasks on them and see what happens. So it's a great idea to try and get more, elicit more state, and also, in the end, trait information too.
Mm-hmm. Okay, thanks. The next question is about whether there are different phases in the way that people answered in the Bandit problem. So maybe I'll simply read it. The question says, maybe the participants chose to find a better button by counting how many times they have to press the button until the reward shows up. This would suggest that during the initial exploratory phase, the participants switch when the reward shows up, but in a later phase, the probability of switching might be independent of whether the reward shows up. And then he asked whether you have evaluated the switching gap and whether this is more prominent during the early stages.
That's a really interesting idea. So we've not done that. But I would say that we had these 12 blocks of 40 seconds each. And so it's not so, and then during each block we have we have one of these 3 probabilities of the better bandit. So so it's not that we're only seeing the behavior like this in the very first block, for instance. Now, this is something where we're looking across all the blocks, and you can see that the behavior has this characteristic. So of course, as ever, it's interesting to ask, how is it that to try and get some subjective information about how it is that our subjects are going about making these choices, and the idea that maybe they're trying to count how long they have to wait. But given the probabilistic nature of the bandits, and given the fact that they're being rewarded on these 3 different schedules, on the good choice and on a different one on the bad choice, a single number like that wouldn't work. Now, of course, maybe the subjects are choosing a number as they go. They think, how many times did it take me to get the first reward in this case? And certainly in other bandit tasks, we've known that the early exploration behavior has a big effect on what happens later. So it could be really interesting to then now take the analysis that we've done and say, now can we go and get a much finer characterization of the behavior? And indeed, I think one of the things, as I argued for the first case, in the end, I'm not satisfied with these RNN models because they're complicated models. They might give us ways that we can relate to neural behavior, but they don't give us the depth of understanding we want. So what they are is really an embarrassment. They say, if you can't predict this well using your mechanistic models, you made mistakes. So it's great to have these sorts of suggestions where we can now say, okay, let's go and look for that. How much more of the behavior can that explain using this? And I think that's a really interesting idea to have a look at.
Mm-hmm. Okay, thanks. The next question is about this latent representation, your autoencoders. So the question is whether what are the methods to test if this latent representation is a valid description, and in particular, how stable are the Euclidean distances in Z between the 2 subjects after retraining the whole mode?
So I didn't understand the last bit. So after retraining,
the whole mode, that's what it says. But I think the most important part is probably the first part of the question. So how do you know that the latent representation is really a valid description?
Yes. So we have done some work looking at training on half and then to training 1 half, and then looking at the underlying representation in these spaces. We've looked to see whether you can discriminate which sort of subjects you have. So, for instance, is it a valid way we train all the subjects in all these 3 different categories on these in the same model, and can we then classify the subjects based on that latent representation? And indeed, as I argued, we can see there's actually other substructs that we'd love to go after, like these in the bipolar cases were particularly spread around that case. And then we can look to see whether the behavior that gets generated is reasonable characterization of the behavior that happens. So, for instance, as we manipulate Z2 into the regime that we think of where our bipolar patients are, does that generate other statistics, statistics which are similar to the subjects? And then we're in the same realm that we heard about yesterday, these sort of notional sufficient statistics that you can have for these complicated simulation-based models that we heard about from Jakob and from Kyle as well. And I think it's interesting to think about how is it other ways of validating the behavior. So that's something else that's on our mind. And then, of course, we had these goals for the representation. So how well, how far is the MMD? How closely characterized are they by the prior expectations we have in those dimensions? What we've also done, of course, is to look through cross-validation to see how many dimensions do we need to explain behavior well. So we do cross-validation in these models too. So we're just throwing the same set of spaghetti against the wall and hope that something sticks.
Okay, so did you also try, for example, whether if you cluster this representation that you get independently from the labels that you already have, whether you would sort of recover similar groups like bipolar versus healthy patients or so, or whether such a clustering algorithm would give you completely different groups?
Yes, so we've not tried clustering, and that's essentially one of the next things we wanted to do. And one really important thing to point out is, of course, these groups are themselves very coarse groups. So one of the hopes of computational psychiatry, now the general field of which this is a little bit of part, is that we can find different ways, and perhaps hopefully maybe even better ways, of characterizing aspects of the way that subjects are performing these tasks, but maybe then the way that they also, things that they would experience in the world. And then things like the adversaries, you could imagine using that to try and find an adversary which will help us classify what the subject is actually like, and so get a better understanding. And then look at that, how does that relate to other things that we might be able to characterize about the subjects as, like in the end, hopefully things like what improvement we might do. So the very, very, very long-term picture is indeed exactly that we would like to look at clustering in that space. So we haven't done that yet, and indeed 30, it's a rather small number of subjects. It's quite a lot, to collect these subjects in this way is not so easy. But we'd obviously like to do that with much larger data sets, and then we'd have a much better picture of what the overall architecture is like. One of the great things, or one of the important things that people have found these days is using things like mTurk, is that you get on mTurk subjects, although they're essentially healthy subjects, most of them you see just slightly higher social anxiety, not much when people have done the psychometrics. But what you see is you get these big spectrums along many of the psychiatric dimensions, so they're not at exactly the margins of the dimensions that you would see for people who actually have full-blown disorders. But it allows us through online platforms, for instance, to collect a larger number of subjects that we could then relate to the questionnaire measures they have. So people like Claire Gillen, working with Nathaniel Dorr, have done this very successfully for looking at OCD, so obsessive compulsive disorder. And I think this is now something we could do with versions of these sorts of Bandit tasks, feed the data from that into our models, and then look to see what happens in terms of this cluster structure, for instance, that would come out.
Mm-hmm. Okay, thank you very much. So I think we have asked many questions already. So I think we maybe take a bit of time to transition to the next session. So thanks, Peter. Thanks very much for your talk and for answering all our questions. So our next speaker is going to be Dominic Papis in 2 minutes, and the tech team just needs to transfer us all to the next session. So all of you don't have to do anything. You're just going to be transferred. Thanks, Peter.
Thank you very much, Ulrike. Thanks very much to the audience. Thank you.